Okay, one thing we didn't get a chance to go over in the last lecture was the idea of efficiency. Efficiency, when you're dealing with energy delivery, is the measure of the desirable outcome of an energy work conversion relative to the undesirable outcome. And so, you know, how much of the energy goes to where you want it to go, how much goes someplace else. You know, for an example, if you're talking about converting electrical energy in a light bulb, the desirable outcome is light. The undesirable outcome is heat. For a furnace, it would be just the opposite. You want to convert the, say, electrical energy or the chemical energy from burning the fuel into heat, and the undesirable outcome is light. For an incandescent light bulb, the Edison-style light bulbs, actually only about 10% of the electrical energy is converted into light, and about 90% of it goes into heat. Well, you know how hot those things can be if you touch them while they're on or soon after they're turned off. They're really hot, and actually a vast majority of the energy goes into heat rather than light. So that would only be about 10% efficient. On the other hand, something like an LED light, it's pretty much the other way around. About 90% of the energy goes into producing light, and only about 10% goes into producing heat. So those would be considered about 90% efficient. Okay, there's energy flow, you know, which has to do with moving energy from one place to another. To change the energy of an object, work might have to be done against one of the following. One thing might be inertia. If you're doing work against inertia, you're changing the kinetic energy of the object. Another factor you might have to do work against is gravity. And that would change gravitational potential energy. You might have to do work against the shape. For example, for springs or elastic materials. So say the energy that's stored up in a coiled spring is considered to be potential energy. And when you stretch the spring out, you're actually changing the amount of energy that's stored in the spring. That's changing its potential energy. Another thing might be friction. And friction is basically what's changes kinetic energy into heat or sound. And a good example of friction is just rubbing your hands together. You know, when you go like that, you can feel your hands getting hotter. You're converting the kinetic energy of the movement of your hands into heat, that's for sure. And also you can hear it. And so some of the energy becomes sound. Or any combination of the above. All right, when we talk about energy, we've divided them into potential and kinetic energy, but there are actually 6 forms of energy within the area of potential and kinetic energy. And these are known as the 6 forms of energy. And each of these will, in addition to what we call it, it will also qualify as either potential or kinetic energy, or in some cases, it might be a little of each. So among the 6 forms of energy, we have mechanical energy. Mechanical energy is the energy of everyday objects. Moving objects. For example, stretched or compressed springs. Machines, motors. Animals, us, all have mechanical energy. Mechanical energy can be either potential energy or kinetic energy. As you may have noticed from the things I named off, moving objects, that's kinetic energy. But compressed or stretched springs, that's a kind of potential energy. So actually mechanical and most of these others would be kinetic energy also. So that could really be either one. Another one would be chemical energy. Chemical energy is the energy stored in chemical bonds. Basically the hold elements together in compounds. And this energy can be released through chemical reactions. And this is a form of potential energy because it's an energy that's related to the condition or state of the matter, but it's an energy that's sort of stored up most of the time. There's also nuclear energy. That's the energy stored in the nucleus of an atom. And in order to release this, you need a nuclear reaction. And this is a type of potential energy. Radiant energy is the energy transmitted in the form of electromagnetic radiation. For example, infrared, which is the energy that we feel as heat. But other types of electromagnetic radiation would count as radiant energy also. Because the waves are moving, the electromagnetic waves, that is, are moving, this is considered a form of kinetic energy. And sixth is thermal energy. This is an internal energy that all objects have above absolute zero. Absolute zero, of course, being 0 Kelvin or negative 273 Celsius. And it causes vibrational motion of the atoms. And the warmer something is, the faster the atoms vibrate. This is also known as heat. And because it involves vibration, that is movement of the atoms, it's considered kinetic energy. Okay, so to look at those 6 forms of energy again, and this time just dividing them up according to which ones are kinetic energy and which ones are potential energy. We said before that mechanical can be either one, depending on the specific instance. Electrical energy, and it is kinetic energy because it has to do with electrons moving through a wire. Radiant energy is also kinetic energy because it has to do with movement of electromagnetic waves from one place to another. And thermal energy also is kinetic energy because it has to do with vibration of molecules or atoms. So kinetic energy is the energy of motion. Under potential energy, we have, again, mechanical energy, but we also have chemical energy. And nuclear energy. And this is stored energy. And that requires something to happen to release it. Okay, so we've seen the forms of energy. Sources of energy. Source of energy, we have many different sources of energy, of course. And there are various ways to classify various sources of energy. One of them is renewable versus non-renewable. Renewable energy are sources that are able to be replenished in a short period of time. Okay, so, and now it begs the question of what is a reasonably short period of time? It usually has to do with something that's sort of on the scale, more or less, of the time it takes to use the energy. So some examples of renewable energy would be wind, solar, biomass. So that would be like composting energy or extraction of methane from garbage dumps. moving water, like hydropower, like Niagara Falls. Kind of on the borderline of being renewable would be wood, because of course you can grow more trees, but it takes a while. Yeah, so it definitely takes longer to grow a new tree than it does to burn the wood from the tree. But that would be kind of sort of on the borderline between renewable and non-renewable. And then we have non-renewable energy. That is, can't be replenished in a reasonable time. So these are limited in supply. And not replaceable in a reasonably short time. And some of these would be, for example, fossil fuels. And fossil fuels would include things like oil, coal, and natural gas. And fuels derived from any of these three. So things like oil gives us gasoline and diesel fuel. So they would qualify as not non-renewable. And coal is related to things like peat. So, if you're burning peat in your fire, that's basically the same thing as burning coal. That's non-renewable. And the energy sources that are most commonly used and this is in the US, would be petroleum products. And these are fuels for basically everything. This would include power plants and factories and cars and trucks and ships and basically any kind of energy need. So petroleum products supply about 40% of our total energy needs. Coal is about 23% and headed downward. Natural gas is about 23% and headed upward. And that's pretty much why coal is headed downward. It's not really economical to use coal anymore because natural gas is so cheap nowadays. Nuclear would be about 8%, and that's also headed downward. Hydroelectric, would be water. That's about 3%. And other would be about 2% and headed upward. Because other, in this context, would include wind and solar. So, we're expanding use of those sources of energy while reducing certain other ones. Every source of energy has its pros and cons. None of them is all good or all bad. And so that's why we have such a mix of different sources of energy. What I'm getting at now is there are a couple of different ways of measuring efficiency of different types of energies or power production. And one way would be energy density. So energy density would be energy output of the fuel per unit of volume. Typically in engineering, at least until fairly recently, engineers like to use English units for some reason that escapes me. As a chemist, I'm used to using metric units. And once you get used to using metric units, you really can't believe that anybody would ever want to use English units. So anyway, the units would be BTUs per cubic foot, or if you want to use SI units, it would be joules per cubic meter. And BTU stands for British Thermal Unit, so that is very much in the English system of measurement. And it is defined as the amount of heat that's required to raise the temperature of 1 pound of water by 1 degree Fahrenheit. Okay, so it's similar to the definition of a calorie, but it's in English units instead of metric units. Okay, and 1 BTU, the conversion factor, is 1 British thermal unit is equal to 1,055 joules. So some examples. Diesel fuel has an energy density of 1,060 BTUs per cubic foot. Gasoline has a density of 920 BTUs per cubic foot. And propane has an energy density of 680 BTUs per cubic foot. So there's energy density. There's also power density. Energy density is actually more about the fuel. Power density is actually more about the power plant. And so the power density is the amount of power delivered per unit of area, like floor space. And you can sort of estimate what these values are for different types of power plants, because the power plants of a given type kind of have a fairly standardized design, and so you can kind of estimate what the energy output would be for a given number of square feet, and you can get your energy output that way. Remember that power is energy or work per unit of time, and units of power density would be watts per square meter. Yeah, suddenly we're back to using metric units again. Square meters would be floor space, or basically the area of the plant grounds. So for example, a typical coal plant would have a power density of about 1 kilowatt per cubic meter. Natural gas plants would have a power density of more like 4.5 kilowatts per square meter, considerably more than a coal plant. That's largely because coal plants usually have to keep a large amount of coal on hand, and coal is a solid, and it comes in chunks which don't always pack together very efficiently. So there are a lot of air spaces in with the coal that's being stored. And so that takes up a lot of space, and a lot of that space is actually air. Whereas natural gas for a power plant is usually either piped in which case they don't have to store any of it on the grounds, or it can be stored in a compressed form as a liquid in tanks. And that is very efficient because the molecules are very close to each other and there are no air spaces between them. So really, it's a very efficient way of storing things. Wind, on the other hand, is about 7 watts per square meter. Not kilowatts, but watts. And that's largely because wind turbines are not all that efficient yet anyway. They're improving. But the amount of space that a wind turbine takes up is pretty substantial compared to the amount of power that it actually produces. So that would be the lowest of these three anyway. For generating electricity, why don't we start that in the next segment of the video, because we're at about 30 minutes now. So I'll see you in a moment.